Hi everyone, welcome to part 2 of section 4.4. So in the remainder of section 4.4, we're going to be looking at the exponential distribution and then we will introduce the chi-square distribution at the end. So let's start from the beginning, the exponential distribution. I've broken it up into three main sections. So the first section we're going to look at is just an introduction. We will need to look at the PDF, CDF, and the moment generating function, as well as how to find probabilities. And then we will also have a look at how the exponential distribution is related to the Poisson process, and we will look at the memoryless property and its proof. Let's start off by just introducing it. So, the exponential distribution is a special case of the gamma distribution, specifically where you choose alpha to be equal to 1 and beta to be equal to 1 over lambda, where lambda is just some value greater than 0. This is the shorthand notation that we use for the exponential distribution. Note we only have one parameter because we only have the freedom to choose the lambda. The alpha is fixed. So in general, we can say that a gamma with these parameters is equivalent to an exponential distribution with parameter lambda. Hopefully you remember from the previous video that the gamma distribution takes on two parameters. The first parameter is your shape, and then the second parameter is called your scale parameter. The shape parameter is fixed to 1. So if you look at these examples of gamma distributions with different values of alpha, you will see that when you fix alpha to be equal to 1, you get this shape. So you can expect that exponential distributions will have that shape. And you can see from this graph, figure 4.27, that they all have that same exponential curve. Now, when would you want to use an exponential distribution? I'll give you a few examples, but in general, it's going to be in cases where most of the probability is loaded on small values, and then it becomes rare and rare and rarer to see values that are larger. So for instance, this could be waiting times between events, and these events could be arrivals of customers or calls made to a call. So let's say you have a customer who arrives at your shop. The amount of time you have to wait until the next customer could be something between, let's say, 0 to 2 minutes typically, if I assume these are minutes. So most of the probability is lying between 0 to maybe up to 3. And then the amount of time until you see the next customer becomes less and less likely to be larger and larger values. So clearly this is quite a busy store. And then if you talk about call centers, it's pretty much the same interpretation as well. The chance of having a long period of time between calls is lower than having something in this interval. So it just depends on which lambda you choose. So you can see for lambda equals 2, most of the probability is between like 0 and 1. And then for lambda equal to zero point 0.5, it spaces it out a little bit more, so you have more probability being assigned to, let's say, up until 3 or 4, and then less and less beyond. So it really depends on what case you have. Another example is component lifetime. So let's say you've manufactured something, or maybe you have some machinery that functions for some period of time. And we're saying the lifetime of that machinery or that component you've manufactured is typically going to be within this time period. And then it becomes less and less likely that the machine or component will survive for extremely long periods of time. Now let's look at the PDF. What does it look like? What I have here is the gamma distribution. So remember I said the exponential is a special case of gamma, specifically where you have alpha equal to 1 and beta equal to 1 over lambda. So let's substitute alpha and beta into this function and see what we end up with. So if you substitute your alpha in this case, you lose the x because it's x to the power of 0, and you also lose the gamma 1, and the result is this. So you're left with 1 over beta. But beta equal to 1 over lambda, as is given there, is the same as lambda equal to 1 over beta if you just rearrange it. So that means you can replace the 1 over betas with lambdas. And this is the final PDF that you get. And this PDF is defined as your exponential distribution. So more formally, if you have a random variable x, it is said to have an exponential distribution with parameter lambda for lambda values greater than 0 if and only if the density function x is of this form. So if you find a PDF that looks like this, maybe for different values of lambda, as long as they're positive, then they all belong to the exponential family of distributions. So remember, PDFs are unique, just like probability mass functions. So if anything looks like this, it's exponential. Let's now look at the CDF. All right, you need to be able to derive it, and if you would like, I think you should go ahead and pause the video and try to derive it on your own, because this is something you should be able to do by now. Okay, so hopefully you managed to get that you have two regions, okay, and you need to give me the probability of x less than or equal to x for values of x in the different regions. So for the first region, there is no probability to the left of 0, as you can see from the PDF. So you can straight away go and write 0. And then for values of x that are greater than 0, the curve is present. There will be area under the curve. So you will want to integrate from 0 up until the value of x. So we're starting from 0 because we know that there's no area under the graph for values below 0. So we start at 0 and then we need to integrate up until the value of x. And this is just your PDF. Now notice here, instead of using x like we have there, we're using t. And this is something that's important. Make sure you use a different letter. If it's y or z, it doesn't matter. As long as you realize that x is reserved to represent this value. So you can't use x there and then use x here as well. So remember to use a different letter as a placeholder there. And then from here, you just need to integrate and then this is going to be your integral. And in conclusion, this is the final result you get, and you can summarize it as follows. Okay, so this is what the CDF for the exponential distribution looks like. We also need to know how to derive the moment generating function. And once again, this is something you should also be able to do by now. So I recommend you pause the video, try and see if you can get it for yourself before we go through it. Okay, I hope you did attempt it just to get some practice in. This is where you would have started. You always start with the definition, whether it's discrete or continuous. If they say derive a moment generating function, you always start with the definition, which is the expected value of e to the power of xt. Now, since it's continuous, we're going to integrate, and then we take our PDF times e to the power of xt, which gives us this result here. So if you now integrate, before you do that, you can actually take out lambda and then just leave the parts that depend on x. And then the integral is going to look something like this. Now, this is one of those special cases where you need to restrict the values of t so that this whole integral is defined. So specifically, you'll need to make sure that lambda is greater than t, or in other words, t less than lambda. And that'll ensure that you get a function that has a closed form. It's not going to go to infinity. So this means that that term will become 0 and minus 1 if you substitute these bounds. And the final result will be lambda over lambda minus t for t less than lambda. So I hope this is what you got. If you did get it, well done. Another thing that you need to be able to do in relation to the moment generating function is you need to be able to derive the mean and the variance using the moment generating function. So try that for yourself. The same way that we looked at how you do this, Make sure you can do it. You should be able to do it by now. And the answers you should get is mu is equal to 1 over lambda and sigma squared is 1 over lambda squared. And these results make sense, considering that the exponential is a special case of gamma, where alpha is equal to 1 and beta is 1 over lambda. So if you put alpha in there equal to 1 and beta equal to 1 over lambda, it gives you this result. And then if you do the same thing here using the formula, you end up with the final answer. So just make sure you can derive these results using the moment generating function. Now that we've introduced the PDF, CDF, and MGF, it is time for us to look at how we find probabilities. Now, at this stage, you should be able to find probabilities. The method you're going to use here is a method that we've already looked at. Okay. So I'm going to give you a chance to look at this on your own, but just a few hints before you do that. A quick reminder. So remember, if you want to find probabilities for any continuous distribution, then you're going to integrate under the PDF in the relevant region. Now, this distribution, it's not like your gamma and your normal, which are difficult to integrate. Therefore, they're already tables where they've done the integration for you. Here, you have a nice function which works out for you to integrate. So there are no tables, all right? So try to do this example. Pause the video now, see if you get it, and then we'll have a look and see if you manage to get the correct answer. Okay, I hope you did attempt it. The answer that you should have gotten is 0.449. So let's have a look at how you should have done this example. Okay, so to get that answer, let's take it step by step. Step 1, let's define our random variable. They told us in the question that the survival time of these mice follows an exponential distribution. So your survival time is your random variable. And then the second thing you need to do is identify the distribution that you're using and the parameters. So they told you in the question that it's exponential, so that's already a good start. So what if you want to find the parameter? The question says, without treatment, the expected survival time was 10 hours. So in other words, it says the expected value of x is equal to 10. So just be careful. Don't, when they give you the expected value or your mean, that is not your lambda, okay? In this case, lambda is equal to 0.01, and this is how you get it. Remember, the expected value for an exponential distribution is 1 over lambda. So if you make this equation and you solve for lambda, you end up with 0.1. Okay, so be careful. A lot of students make that mistake where they just take the mean as the parameter, which is not correct. Okay, so in conclusion, that means x follows an exponential distribution with parameter 0.1. Now the question is saying what is the probability that a randomly selected mouse will survive at least 8 hours? And as I mentioned just now, there are no tables for this process. So you need to find the PDF and then integrate. Find the area under the graph. So this is your PDF. So you will be given this in your formula sheet. The parameter is 0.1. So everywhere you have lambda, you put 0.1, and this is what you should end up with. The question says, find the probability that a randomly selected mouse will survive at least 8 hours. So minimum 8 hours. So 8, 9, 10, anything. Minimum 8 hours. So if I were to draw that, then it would look something like this. So this is my exponential curve. And then remember the probability is given by the area under the curve. So we want all the area from 8 onwards. And this PDF doesn't have an upper bound, so when you integrate, you'll just integrate from 8 to positive infinity over this PDF. And then that is how you'll get the answer of 0.449. For another example, have a look at example 4.29 in your textbook. The last thing we want to cover in this video is the relationship between the exponential distribution and the Poisson process. As I have already alluded to, the exponential distribution is closely related to the Poisson process. It is frequently used as a model for the distribution of times between the occurrence of successive events. For example, customers arriving at a service facility could be an event of interest, or even calls arriving could be an event of interest. So we're saying that the time between successive calls or customer arrivals can be modeled according to an exponential distribution. So before we look at the details, I want to just give you an overview of what this is saying. So suppose X is the number of customers who arrive. Let's assume that they are modeled according to a Poisson process. So if we focus on, let's say, this 1 hour period, we're saying the first customer can arrive at that point in time. And then a few minutes later, another customer, and maybe a little bit later, we have other customers who also arrive. Now, the times between the arrivals can be modeled according to an exponential distribution. So, in other words, the time between customer 1 and customer 2, we're saying that follows an exponential. Similarly, the time between customer 2 and 3, and so on. So, let's say I label these intervals W1, W2, W3. Then obviously these values can take on different positive values. So this could be 5 minutes, it could be 20 minutes, it could be 10 minutes. So obviously the time between successive events is a random variable. And we're going to look at a proposition that tells us that these times can be modeled according to an exponential distribution. In the textbook, on page 199, the following proposition is introduced. I'd like you to just take a moment to read through it. Try to break it down for yourself and make a note of things that might not be clear to you. And then I'm going to go through it in the next slide and just break it down for you. But just read it for yourself now before we go into it in detail. Okay, let's see if your understanding is correct. So what I'm going to try to do is I'm going to take this paragraph and try to summarize it into fewer words. All right, so let's start off with the first sentence. Suppose that the number of events occurring in any time interval of length t has a Poisson distribution with parameter alpha t. All right, so in other words, I'm going to rewrite this as let x be the number of events in time t such that x follows a Poisson distribution with parameter alpha t. Okay, and this notation of alpha t was first introduced on page 150, so just go back there to refresh on it. Now, I want to jump to the last sentence here. We'll come back to the stuff in the middle, and then let's go straight to the conclusion. So, suppose this is true. The next sentence then says, then the distribution of elapsed time between the occurrence of two successive events is exponential with parameter lambda equal to alpha. So, in fewer words, if W is equal to the time elapsed between two successive events, so remember those events could be arrivals of customers, it's saying that this time follows an exponential distribution with parameter alpha. So this alpha is specifically the same alpha as the one given in there. Okay, so in a nutshell, this entire paragraph is just trying to tell you that if you have this situation where x has a Poisson alpha t, then the time between these events is an exponential alpha. All right, I want to now have a look at it in a little bit more detail. So let's start off by just looking at that first part where you have that alpha t. So I know some of you will tell me that you've never seen this in your life, and it doesn't matter, I've got you covered. So I'm ready for such situations. Anyway, so let's look at this example. The number of customers arrive at a shop at an average of four customers per hour. All right, so this is some Poisson process. You have 4 per hour. So just put back in your chapter 3 brain. And one of the questions you could have been asked is what is the probability of exactly two customers arriving in, let's say, a given hour or a 2 hour period or 30-minute period? Okay. So in all these cases, let's just agree that we're asking for x is equal to 2. So it's exactly two customers. All right. And if you wanted to now find the first probability in A, you would now use a Poisson with parameter 4, okay? Because this is 4 per hour, all right? So that's what you do in this case. What would you use for B? Like if you wanted to find the probability of two customers in a 2 hour period, okay? This time was given for a 1 hour period. So if it's a 2 hour period, then you're going to use a Poisson 8, right? Now for the last one, you're going to use a Poisson 2 because it's half the time. Okay. So what I want to just highlight with these examples is now, okay, how do we get the 4, the 8, and the 2? Okay. It was all dependent on this time that we're focusing on because we're given a rate per hour. So we needed to adjust it according to the period of time that we're looking at. And how we got these, let's say this is lambda, all right? So how we got the 4, you can think of it as saying 4 times 1. Okay, because it's a 1 hour period. And then the one where it's a 2 hour, it's 4 times 2. And the other one where it's 30 minutes, in terms of hours, that's half an hour. So it's 4 times zero point 0.5. So that gives you your 482. So in general, suppose I gave you any time interval, you are going to take the parameter equal to 4 times t, where t is some time in hours. Okay, so in general, for this particular example, my x always followed a Poisson with parameter 4t. Okay, so if you compare this with that notation, in other words, that means your alpha is equal to 4. All right, so that's where that comes from. So if you get a question, you can always write it in terms of alpha t. So the important thing is you need to be able to identify what your alpha is because remember this alpha becomes your parameter for your exponential distribution. All right, so that's the first part. Now let's have a look at the next part. So it says suppose you have this Poisson distribution with parameter alpha t, and the number of occurrences in non-overlapping intervals are independent of one another. Okay, we're going to just break down that part. So suppose we're still looking at this shop example, all right? So it opens at 9, and then these are different time periods throughout the day. So you have customers arriving in different time periods. Okay, so the first word here is non-overlapping. So I've divided it such that these times don't overlap. So 9 to 10 does not overlap with 10 to 11, etc. So we're saying customers can arrive, let's say, in different hours. You could have one customer in the first hour, you could have two, one, it doesn't really matter. So there are different numbers of customers. And what the statement is saying is that suppose that the number of occurrences, so in our case, the number of customers who arrive in non-overlapping intervals is independent of one another. So in other words, the number of customers that arrive in this interval is independent of the number of customers who arrive in this interval. So the fact that we saw two customers here has no impact on how many customers we'll see in this interval, in that interval, as long as the time intervals do not overlap. Okay, so that's just what that middle sentence is trying to say. Okay, so now the last sentence is the one that I have written in this form, so it's pretty much almost word for word. Okay, now let's look at the whole thing put together. So we're saying if I have some event that follows some Poisson process with parameter alpha t, so it could be the arrival of my customers, so the number of customers that arrive, let's assume they follow Poisson parameter alpha t. All right. Then what this proposition is telling me is the amount of time between customer, let's say 1 and 2, is exponential with parameter alpha, and it's the same alpha as the Poisson process that the people are following. Okay, I think we're at a place where we can do an example now. I'd like you to try this example on your own, considering everything we've just discussed, and let's see if you can get the correct answer. So it's a direct application of that proposition. Okay, I hope you pause the video and try it on your own. The answer that you should have gotten for part A is that x has an exponential 2. And then for part B, the probability is 0.01872. All right, so let's have a look at how you should have done this one. Okay, so we start off where I always recommend. Let us define our random variable. All right. In this case, we've already been given x. So x is the time elapsed between the arrivals of two successive customers. But they didn't give us a letter for the Poisson process. So I want to write that one first. Because remember, once we figured out what the alpha is from the Poisson process, we can now find the parameter for the exponential. So let's start off there. So let y be the number of customers arriving at a grocery store. All right, so I just copied that from here. And we know that the number of customers that arrive at the grocery store is a Poisson with parameter 2t. So that means it's two customers per minute. So that means T is time in minutes. We are given that X is the time that elapses between the arrivals of two successive customers. Okay? And according to the proposition that we were given, if you have some Poisson process with these parameters, then the amount of time between successive events is exponential with parameter alpha. In our case, alpha is equal to 2. Therefore, the amount of time between um, arrivals of two successive customers is exponential 2. All right. I hope that is how you worked out this one. So let's move on to part B. Okay, so in part B, they're saying what's the probability that the amount of time that will elapse between the second and the third customer's arrival will be between 2 and 5 minutes. Okay, so just something I want to highlight before we even go on with this question is we've specifically chosen the second and the third, but it could have been the fourth and the fifth, or the eighth and the ninth. The fact that they follow one another makes them successive, but it doesn't matter, whether it's the first or second or the third or the fourth, it doesn't matter. The fact that they're just two people, that two events that are successive is what really matters. Okay. So this is not something for you to get confused about. Now you just want to focus on the fact that you know from the proposition that time between events follows an exponential distribution. So this question is saying, okay, what's the probability that that time, so in other words, x, is between 2 and 5? And we've already looked at how to find probabilities for the exponential. Remember, there are no tables. So you need to integrate from 2 until 5 over our PDF. And in this case, lambda is equal to 2, so you just substitute in the PDF and then you'll integrate. Now, if you know what the CDF looks like, let's say it's this, so maybe you would have derived it earlier in the paper, then you could have used that F5 minus F2 and you would have gotten this answer. Okay, this result is not given in your formulas. You're only given the PDF. So you can always work it out this way. And I recommend you always show all your working so that if you do make a mistake somewhere, then you can still get part marks. In your textbook, there's example 4.30, which you can also look at, and it's an application of this. So now we have reached this point and we're left with the memoryless property when it comes to the exponential. So I'm going to end this video here and we're going to look at this part in part 3 of section 4.4. I hope you enjoyed this video. I'll see you in the next video.